Welcome to physics. Physics in the AM. Joel Sandalka here. And the vectors are getting down to it. Okay. We have talked about projectile motion, and a logical extension is circular motion. Why does this extend from that? Well, let's do a thought experiment for a second here. And the title, yes, uniform circular motion. We'll think this through a bit. Some of it won't show up on the video very well. Now, ignore the writing here, but I'm just using it for the circle. Why don't you put a circle? I'm going to just get another circle here for a second. It's up there. Okay. And I've talked to you about this before. But imagine. Still imagining. Okay. This is the Earth. And it doesn't have to be the North Pole at the top. This could be the equator. It could be around, whatever. If I had on the Earth a mountain, and I had a shot, a cannon that shoots, you think it'd go like this, right? Boom, hits the ground. Far enough. Don't draw this. Just watch this. We'll get it all. Somewhere. Okay. Well, what if I shot it a little bit further? Okay. We'll go like this. If you notice, like, normally when we're talking projectiles, we're talking short range, so you think of the Earth as flat for that section. But if you shoot it fast enough, by the time it falls and where it should have hit the Earth is curved away. You guys follow that? If I shoot something fast enough, throw something fast enough, propel it fast enough force, by the time it falls, the Earth is falling away. Now, remember, there's really no up when it comes to gravity. It's always gravity sucking you into the center of the Earth. Now, it's here. The force of gravity is pulling to the center of the Earth, but it's going to continue falling towards the Earth. But every time it gets closer, the Earth is curved away. Think of it as straight there, down there. And then you follow what I'm saying like that. And then this section, right there, and then down. Okay, I'm not drawing it well, but if you think of it as little breaks, it's falling a bit and going sideways a bit. And the Earth is curved away. Well, that is circular motion. I'm just going to erase that. Right. Now, this is the best diagram. With circular motion, one of these pendulums. Heck, I'll do them all. No, I won't. Forget me. And this won't show up on the video, so I can just pause it anyways. We can swirl it around and we'll think about it. So when I'm twirling that string, if I let go of the string, where will that stopper at the end of the string go? Will it go straight out? Will it shoot out like this, or will it do a curved motion? What will happen? Well, is to twirl it and let go. Straight? Okay, which fly straight then? Straight like this or straight like this? Straight, like the first one. The first one? Yeah. To the right-ish. Yes. Okay. And you guys convinced just because he said it? It will not, it will be a straight path. Now I'm ignoring the downward part because of gravity. It will go down, but if I do this, it's hard to see. It's going to be a straight path, and I'm not going to do it too much. Like, keep your head up. I'm not going to try it. Wait. I'm going to let go of it. And we're going to see it. Let's go on a straight path. I'm trying my hardest not to. I kind of threw it. Okay, now you guys watch out, because I'm not gonna. That went pretty straight, good, yeah. Other than the downward part of that, right? Okay. So that means, I just showed you that because I want you to be convinced that at every second, it's actually a tangent. You guys are familiar with the word tangent? Right? Basically 90 degrees to the radius of the circle. Okay? And then the next second when it's over here, the velocity is actually right there. And then as it continues around the circle, the velocity is there. The velocity vector. Every second, like that, right? And I have the bicycle tire out because essentially each part of the tire is this added up for the angular momentum at all times, right? When it's spinning. But we're not going to talk about the concept of momentum. We're familiar with this circular motion. So something right here, something right there, straight down, here, straight across that way, straight up right there. Draw this, and we're going to talk about it. Because there's some forces we've got to have some names for these. There's a fictitious force called centrifugal force. And I say fictitious because it's kind of imagined. Now, it's easiest to think if you're on like a merry-go-round kind of ride at the exhibition or somewhere, right? You're going around. You feel a pull out. You guys follow if you're going in that circular path? You guys know what I'm talking about? Because typically, nobody drives their car in a circle fast enough, I hope not, that they feel that pull for like 5 minutes. So, okay, but talk to us then. Okay, the Polar Express, is that one where you, okay, is that the one where they play music all the time? Right. Oh, and it's, oh, that's a sick one. Yeah. Makes you sick. But yeah, do they still have the rotor? Where you get stuck to the wall and the floor drops out? You guys follow that? Or like follow what I'm talking about? Okay. Now think about that one. Is that, you think of it as, I'm being sucked to the outside, there's a force pushing me out. That's called a centrifugal force, and that's a fictitious force. It's really that you are, if you were to let go at any given time, your natural tendency is to fly, right, that, like that, right, out. But the wall is stopping you from flying out. You're spinning around. So it's actually an inward force. We think of it as outward force. That's why we're not going to talk about that before. Like, I'm not going to talk about it in physics too much because it's centrifugal force. You think this is the centrifugal force idea, the fictitious force. That something's pushing you out to the wall. If it's going around and you're stuck to the wall, right? Now, it's really that if you're stuck here, you're the person, that the wall is pushing you in, keeping you from flying away. And so, you're right here. You're actually being spun. Now, the real word that we're going to use is not centrifugal, but centripetal force. And that's an actual physics force. It's not this fictitious. Centripetal acceleration, centripetal force. So I'm going to put it right here. I don't care where you put it. Centripetal force. This is not a vector because it changes direction every second. We're going to call it FC. And it's the mass times the centripetal acceleration. Okay. Now, how do I figure this out, though? The circular acceleration, the centripetal acceleration is d squared over r. I'm going to just tell you that. R is the radius. And v without direction, because it's changing every second. It's spinning around. So it's really speed squared over the radius. Intuitively, you know this. The faster you go, the more acceleration, the more pull on that string. If it's gravity or if it's an actual string or the side of an amusement park ride or whatever. Let's think about this. We know some geometry. Squared over r. If I was to time, just twirl this again, how can we figure out the velocity? Well, we know how to measure a circle's radius, right? From the radius, you can get the distance. What do we call the distance? Geometry around the circle, not the perimeter. Circumference, right? You know what the formula for circumference of a circle is, given radius? R squared is area. That's okay. Nobody can come up with it now. Grade 8 you did it. And you did that. 2 pi r. 2 pi the radius. Pi times the diameter if you're given that. But, okay, we're going to use 2 pi r. So, to find the velocity, we need to know the distance around a nugget like this. That's the, on blue, what I'm talking about is the distance. So the velocity itself is the distance around. And I don't know if you remembered this, but we have to see here talk about that period of one rotation of one cycle. Remember frequency and period inverse reciprocal to each other? We're going to use a capital T, and that just means the time for one complete revolution. One complete. So, I'm going to put this all together here. So what I'm saying is that if this is the velocity formula, put this substituted in from here. That's what I'm going to do. Centripetal acceleration is also equal to, well, 2 pi r over t squared. So all I did was replace the v with this expression, right? Follow where that came from? I haven't fully worked this out, though. I can simplify it. We don't want a fraction within this fraction. Now, I'm going to write something down, simplify it, but I'm going to do it in a different color because you don't need to write it out. I'll just show you. It's not witchcraft. It's fun. Would you agree the top turns into 4 pi squared squared r over capital T squared. And then when I divide by r, invert and multiply the reciprocal, like of the bottom. I'm erasing. You guys follow what I just did? To divide by the radius, you flip and multiply, right? It goes back to grade 8 and 9. Yeah. into the other, you can do it that way. Now I'm going to come up with one big equation out of it. So this one R here and one of these squared R's I should cancel out. What I want you to write, and I'll do this in red, because the blue is not, that's just work. 4 pi squared over t. Squared, t squared. Depends what information you give. Dominic was just verifying. Can you just figure out the one thing and just do it as a separate thing and then put it in? You can. Yes? I don't know. So I've got 2 acceleration formulas for centripetal acceleration. Got this one, and it's pretty useful depending on what information you give. And this one. Okay? That means our force equation, you know, we said F equals ma, but circular. You can insert. I don't typically give these because it's just inserting the acceleration. Either one of those work. Just depends what information you get. And you're going to solve problems with those. And it's basically algebra. Algebra. No more random time. Okay? Next question that we're going to look at together. So essentially, make sure, is there anything to clarify? Make sure we got the box formulas down. And then the summary will. Oh, wait a second. Okay. Our next thing is when I said ball, but it's a rubber stopper at the end of the string. How fast do we need to be moving so this ball doesn't fall at the top of the circle, right? Stop. And you know, I'm slowing down, and then it's going to drop now. You guys follow? There's a little bit faster than that, right? It depends on you, right? So we understand this from the other home. From the other side. We've got a force spring in this case. I'm going to move that to the top. I'm going to just erase this. I'm asking about the top. At the same time, we know we have a velocity. And I'm going to draw this in here in green. And I could draw it anywhere, but the radius of the circle, we understand what that is, right? That's the distance. That radius is the same in any. So let's consider this. Yep. When I spin this and it's just about to fall, right there, okay, at the top. Gravity's force down is basically at that point where it's just going to fall. It's equal and opposite, right? Like it's equal to the force from the spin. Does that make sense? Now, we are always thinking, because you're familiar with sitting on the swing, of the opposite, the centrifugal force. The force, the normal force of the seat of a swing on your butt, right? And that's pushing you in. So that is, okay. Enough. Are you guys convinced that this part here, at the top of the circle where it's not falling, it just has to be equal. This is just where you feel kind of, just about the weight. Well, I know something about this. The force is mAc, and the gravity force is mg. I'm not worried about signs. This is not vectors. Circular forces, we won't use direction because it's changing over time. So even at the top, I know it's ground. Okay. They're the equal force. Okay. That means, you know what? It's the same whether this, you notice how mass can divide out? So what this means is that something in orbit like this, if this is, I don't know, let's just say it's 0.3 of a kilogram. I don't know what it is. Gravograms. Now, if I made it 1 kilogram, it's still the same speed that it's required. That means that for space travel and stuff like this, orbiting the Earth, it doesn't matter how heavy that spaceship or space station is. That's not coming into play. It does, as far as the fuel concerned, to blast it off into orbit and push it. But to get it to that state, but once it's there, it's the same velocity because it's not dependent on the mass. So I'm going to now simplify this. And we have a formula, and I just gave it to you the other page. E squared over R. And in this case, how fast is it? Well, V, to isolate the part, V squared equals GR. I'll take the square root. We're going to take the positive square root because we're not worried about vectors and so on. Now, what that tells you is gravity, we'll assume, is on the surface of the Earth, 9 point. It's all dependent on the radius. Mathematically, and I'm going to spin this in a second. If the radius is small compared to if the radius is large, which is faster? Smaller. You said it's going smaller? How does this make sense mathematically? I'm going to debate for a minute or two. I'll pause it here. So we aren't talking about the revolutions per second. That's not the speed. It's the actual meters traveled per second. Or centimeters, I guess it would make more sense. Rubber stoppers. Okay. Now, jot this down. I'll read it out so that it's on the video, but jot it down and we'll work it through. Racing on a flat track, no bank. Car going 32 meters per second around the curve, 56 meters in radius. It's caused centripetal acceleration. What would be the minimum coefficient of static friction between the tires and the road needed for the car to round the curve without skidding? If you're on the video, copy this out. I'm pausing the recording. Anyways, racing on a flat track, 32 meters per second, curve, 56 meters radius. That means we need to use acceleration formula v squared over r, not the 4 pi squared r over t squared. That's the information. So v squared, 32 meters per second. Okay, good. Right units. Over 56 meters. And that's a calculator exercise. And I'll bring up my calculator. Well, so 32 squared divided by 56. 18.28. I'm going to go with two significant digits, 18. Now, the units, meters squared over seconds squared divided by meters. Follow that? Right? So you got a single meter over second squared, and that's good, because that's the unit of acceleration. Okay. Think about that. In this case, that's practically twice gravity, almost 2G. 9.8 times 2 is just 19.6. Right? Okay, now the next question is, what is the minimum coefficient of static friction between the tires and the road that would be needed for the car to round the curve without skidding? Oh, goodness. You got to think. The engine is giving it the velocity, but what is giving the car the force that keeps it in a circle? What's the string? What's like the... Yeah, it's the friction, the actual friction in between the tires, the rubber, and the road surface. And if the road surface changes and it's icy, you know this intuitively, you can't make corners on an icy day at the same speed because you have less coefficient of friction, right? You will go flying, and you'll go flying linearly, right? Okay, so what I'm saying is, I'll just draw an arc, is that your car, this isn't quite a free body, it's a bird's eye view of the car. Tires are flat, but anyways, they're like going around like this, right? That's not a vector, that's just a curve to show how you go around. The force itself that I'm interested in is this. Centripetal force. What's providing that centripetal force? Friction. I'm going to put down FC. MAC, which we figured out, so that makes it easy. And we know centripetal force is provided by the friction. So that means FC, force of friction. That's how we connect it. So we have a formula for FC, MAC. We already looked at it. Likely we already have. But we have mu Fm for the friction force. And with tires, unless you're skidding, we don't want skidding, it's a static friction, mu S. You don't have to have the S there. There's always a different value for kinetic and static though. It depends on the brand. Fm, normal. Right? Think about this. didn't get the mass of the car, did I? How are you going to come up with the normal force? Well, the car, we're talking about a horizontal surface, so the normal force is equal and opposite to the gravitational weight force, right? And that's mg. We're going to insert that. U value, mg. What do you notice here? The masses will cancel out, right? So for this kind of a problem, the mass, it doesn't matter. It's not dependent on the mass of the vehicle. When you put mass, by the way, anybody drive a truck in the winter? You guys do anything in the winter to help with the on the ice? You guys put weights in the back? Yeah. You know what that does? It helps you manage, but it actually just changes the center of mass. You follow what I'm saying? It's more front heavy on a truck with an empty box. Then so you put in bags of salt or sand. That just changes the center of mass and it makes it easier to operate so that you're not fish together. That's what that does. It doesn't increase the friction, which some people mistakenly think. So I'm going to cancel these out. Boom, boom. Okay. Try to find the static friction coefficient. So solve for mu. I'm going to left, right, reverse this and call it mu f is equal to, well, I divide the g off, right? So I can put the numbers in ahead of time. But I'm going to put them in now. And here we go. US. What was that answer? 18? You notice the units disappear? And like I said, it's almost twice, so it's going to be a little less than 2. 1.9 is actually what it comes up to. That's pretty high, but anyways. But 32 meters per second, 32 meters per second is actually quite fast. Very fast. You guys know approximately what 100 kilometers per hour is in meters per second? I think it's 28. It's about 28 meters per second. So this is going over 100. That's why this is such a, needs a lot of static, like a high value for the coefficient of static friction. Okay. Now, I'm going to get you guys to try 12, 13, 14 on page 156. Okay. And I'll put them up on the screen too. Wrong textbook here. Okay, these are the textbook questions we want to try, 12, 13, and 14. Run around the bend, what's the centripetal acceleration of runner? Hey, what agent, if you're running around a circular track, what is the centripetal force provided by? Sort of like this car question, but you're not driving a car, it's the, what's it? Yeah, your feet on the ground, between the soles of your shoes. And you know this, you'll wipe out, especially say in a gym, you know that turning quick basketball or whatever, right? Or hockey. It depends on what shoes you have, right? Totally. Okay. Now that's also assuming there's other factors you do naturally too. You lean into your curves and stuff like this too. We're not getting involved there, but there's a calculation to do it. So 13. Car on a flat track, very similar to this one, except a different speed. Same problem, different numbers. I have the same radius though, 56, okay. 14, an airplane traveling 201 meters per second makes a turn. Smallest radius in kilometers that the pilot could make and keep the centripetal. Okay, this one you're given the acceleration. Figure that out. Try those problems. Away you go.